So this is my review video on 16.4, which is Grimm theorem, and it's only a review video because we have already done this for Calc 3. So I will just so what this says is that it's a very beautiful theorem really, because what it tells it gives a connection between a line integral and the surface integral of the surface that the line covers. Okay, so suppose we have a line integral across a certain curve. Okay, so this curve is C. Now, imagine, so this is C, like, I mean, it also covers a closed, it has to be closed. Okay, so simple closed curve and positively oriented, and then the curve encloses a certain region. So what it does is it gives a connection between the line integral along the curve as well as the double integral across the surface. So if you take the line integral m dx plus n dy, all it says is that that is equal to the double integral across the surface covered by C of this function. What function? Nx minus my. So I'm going to use this notation from now on. So nx actually means the partial with respect to x, and my means the partial with respect to y. Okay. So m dx and n dy, so the line integral is connected to a double integral. Let's start with an example. Okay, so let's take this example. So I want to calculate this line integral and across this circle, okay, that is given here. All right, so what is m? M is this part, 3x squared y squared, and n is this part. So we want to calculate, and so we know that the line integral is equal to the double integral nx minus my. So we calculate nx, the partial of this with respect to uh, the partial of this with respect to x, and that is that, and then we calculate my, which is the partial of this with respect to y, and that is so when we my is this, right? Okay, so then we find nx minus my, which is equal to this minus this, and the 6x squared y cancels off with 6x squared y, and we're left with 4x. So this quantity here is actually 4x. So now all we need to do is to take the double integral of 4x across this area, across this region, okay? And we know that it will be easy for us to calculate this because of its nature, right? Because the disk, right, using polar coordinates, right? So what we do is let's put color coordinates, right? And then when we put color coordinates, we want to think about a circle, right, at a distance r, right, from the center. So if you look at the polar coordinates of a point like that, right, so we can write the x coordinate as a plus r cosine theta. So that is your x is equal to r cosine theta plus y, while the y coordinate will be straightforward. It will be r sine theta. If you think of this angle as theta, so r sine theta will be the y coordinate. And then we have an r d theta dr. Okay, so then we have 4 we can take out as a constant, and then x is r sine theta a theta, and there is an additional r coming from the integral r, and then we have dr, and then that's what we have here, r times there, right? And then when we integrate across with respect to theta, then the r cosine theta becomes r sine theta plus a theta, and the limits go from 0 to 2 pi, and then we evaluate that, and then we get r is a constant now with respect to theta, so we put that sine theta 2 pi is 0. When you put the 2 pi here, you get 2a pi times 4, we have 8a pi, right? And then we have the r, right? And then we integrate this with respect to r, and then we have r squared over 2, and we can take the 8a pi outside. Then we put now that integral goes from, because r will go from 0 to a, right? Okay, 0 to a. So the limits are r to a, and then we will end up with 4 pi a cube. So I'm just going to do one example, but I want you to understand the beauty of this theorem. It connects a line integral to a particular double integral. I can write it as a double integral across the region that the curve encloses. It's particularly useful, I think, in engineering applications. If you think of this as a hot surface that you cannot touch the inside, but you can do things across the perimeter. By calculating the line integral of the perimeter, you can get information about, right, integrations involving the region which you say cannot access. And also, it's a good place to remember. So, if this line integral corresponds to a line integral work done from a conservative vector field, then we know that nx minus my is actually 0. So then, as you know, the line integral is 0, right, across the curve. Okay. All right. So that's it for this video, and thank you for watching this video.